As we know, time series forecasting is the use of a model to predict future values based on previously observed values. Basically, in this part, we actually use our previous value to predict our future, that is known as the forecasting. As it comes under machine learning, as we all know, machine learning is one of the most used and popular technique and used by many companies like Google, Ola, Uber. And to keep that in our mind, we came up with a tutorial where you can actually start learning what is time series forecasting, how you can start forecasting your business or maybe the weather as well. Right? So before start the tutorial, let me introduce that Great Learning has come up with a brilliant idea, is Great Learning Academy, where you will learn about almost 80 plus free courses, and after completing your course you can claim your certificate as well. And if you want to do these courses in the mobile application, that is also possible using Great Learning app. So let's get started with the tutorial.
Let's move to the topic of the day. That is about the time series forecasting. So the time series is such kind of a topic. You are going to hit sometime or another. In your career, because most of the data sets are actually time series. So if you go to the factory, if you go to the supply chain, if you go to sales, marketing, you go to any area, let's say some of the typical areas like medicines, the traffic, internet usage. So everywhere you're going to see that the time series is going to haunt you. Okay, so understanding the time series is very important for any data scientist. Okay, now most of the things that we learn through courses or through blogs or through online learning are typical statistical methods. So we are going to talk about all those methods, and we are going to talk about what are the positives and negatives, and then we will look at a problem statement and we'll do hands-on. So it's going to be a pretty interesting session. Okay, so just to tell you the time series. So at least in my career, I have seen two types of time series. One is you see in the left-hand side where you have a continuous signal. So most of these time series you will see in an environment where the sensors are wired together, right? There could be an environment where multiple equipments are working together. It could be in aerospace, oil and gas, or any factory kind of a setup. Or even if you take your smartwatch, or you take your household electricity meter, everything everything will give you some sort of continuous value, some sort of numbers. Let's say your health parameters, or voltage, current. So all these things are continuous variables. So most of the time you will find that this kind of data. And other times you might also find that it's a mixed kind of data where you have a lot of categorical variable. For example, you have some customers and products, and some stores, some items, right, along with the sales value, the revenue. um, let's say you may have some sort of attrition. You may have uh, customer churn. So these type of time series are also very common, where you have a data which is of mixed type, categorical as well as continuous. So sales will be continuous, and product and customer or items, or those things will be categorical. Okay, so most of the time we hit into these two type of time series. Okay, so today we are going to talk about the second type, which is what you see on the right hand side. So why are we talking about machine learning, in the time series context? We have a lot of econometric models like Holt-Winters, ARIMA, right? Exponential smoothing, theta models, and so on. So most of these statistical based models, they work actually pretty well. especially when you have a univariate kind of time series, when you have only one variable. Okay, and statistical models per se will come with few assumption. For examples, they will try to kind of process a time series after making it a stationary time series. So stationary versus non-stationary. Non-stationary is highly variable. It has a lot of local effects, a lot of short-term and long-term effects, right? Where the time series will change abruptly, right? While in the stationary, for the stationary time series, we will try to overcome all these effects and try to make it smooth and nice, right? So most of these econometric models, they work under certain assumptions, and that's one challenge with these type of models. Other challenges, as I mentioned, they kind of handle one time series at a time, right? So if you have, let's say, hundred of customers and thousands of products, and if you are interested in analyzing every customer or every product, then it's going to be very cumbersome for anybody using these type of statistical methods, because you may have to build, let's say, 100 different models, and you may have to really look at each and every model, which is really challenging, almost impossible. So so that is another challenge by using these conventional type of time series model. Okay, now on the other hand, the machine learning model actually score brownie points in that area. So machine learning model, you can build over a multiple time series. So you can build only one model which will cut across multiple time series. And even if you're interested in inspecting, let's say, customer by customer or product by products, or a group of customer and product, you can do that. So you have one model, and you can also inspect customer wise, product wise, and any other groups that you're interested in. So they're very powerful when it comes to scaling, uh, you know, your forecasting methodology. So that is one area. And second area is that machine learning is like a open playground for any data scientist, where you can actually add any amount of features you want to add. So feature engineering is the best buddy for any data scientist, right? And feature engineering uh, can come from some standard methods. It can also come from your domain knowledge. It can also come from the data and some of the exploratory analysis that you do and the knowledge that you spot. I think all of that you can add when you're trying to build your machine learning model. So scaling works at its best when you work with the machine learning model, and the econometric models or the statistical models actually do not give you that much flexibility when it comes to the scaling. Okay, so I hope that this piece is clear, and that is why this topic becomes really interesting. Okay, let's move on to the next. So this context, let's look at a problem statement where we have about 45 customers and around 90 products, and we have a weekly sales data. And along with that, we also have the holiday data. Now, holidays in this particular case are given as an input, but holidays are data points which we can easily extract by looking at the calendar. In fact, we would also be aware of the holidays which are coming into 2021 or 2022. So this is kind of a data which you will have easily available, uh, even in your current context as well as your future context. Okay, so that's make it really interesting. So we are going to look at how we are going to apply the machine learning methodology and forecast the sales for next 12 weeks. Now, I've taken the 12 weeks as a forecast horizon, but it could be anything. It could be 20 weeks, 24 weeks. So that's really flexible. Now, I work with a few capstone projects also with the students, and what I've noticed that sometimes when the scale of customers and products becomes really really big, then it's we try to create clusters, right? We create the customer clusters or product cluster or even a mixed kind of clusters. So instead of customer products, you can think of you can also think of cluster numbers here, cluster IDs, and that also you can use as part of your time series. So it will actually trim the cardinality of your problem. So instead of 4,000 categories, you may reduce it down to, let's say, 50 or 100 categories. But again, when you inspect your clusters, when you inspect the results, I think you need to be very careful, because in that case, you cannot compare customers by customers. You will have to compare cluster by cluster. So let's move on. Our strategy is going to be, we'll look at some of the very basic pre-processing, feature selection, and then we will look at some, the models like XGBoost and CADBoost. All right. Let's go to the data. So I think just to give you a pictorial view of the data, on the right-hand side, you can see that the sales, the trend, the profile, it changes for different groups or for different customers or for different products. So you can see that it's not constant, right? In most of the cases, you will see that the sales profile or revenue profile is actually constant. You have aggregated data for every week or every day or every month, right? And it looks constant throughout the month. But when you try to go a level deeper, try to look at time series customer wise, all cut across all those categorical variables, you will see that the time series look quite different, and no way you can actually fit one single model and justify the forecasting for these time series, right? So that's going to be a challenge for us, and that's where this approach becomes so interesting. Okay. Now, how do we model this time series? And this is you can say this is the crux. This is the heart of everything that we are doing today. So time series modeling, now, this actually differentiate the forecasting to the prediction or some other techniques, supervised techniques, which you might have used in the context of machine learning. So time series, what you see here is that we have a data, let's say 11 months data, and we are forward looking. We are interested in forecasting from 12th month onwards or 12th week onwards, right? So what we generally do, we try to split the data into test, train, and validation, right? And then try to look at the performance of our model. And based on the performance, let's say we pick some model. And then what we are going to do is we are going to predict only the next week or next month or the next day, depending on what is the frequency of your data. So let's say in our case, it is week. So we predict something, we predict the sales next week. Now what happens? We are going to add this prediction as part of a normal data, right? So you can see that the color changes to, back to this green color. So that means now the prediction is taken as part of your normal data, and that, that combined data will be used now to predict the sales for the next week, and so on and so forth. And that's how you actually build your forecast using the machine learning model. Okay, so you basically go unit by unit. So that unit could be a day or a week or a month, depending on how your data is spread out. All right. Now you could have done the prediction at once. Let's say you could have done it for 3 weeks at once or 3 months at once, but then there will be some challenge because uh, you know the period ahead of too much ahead, will not have information of the period which is just before that, right? Because that is also something which is not predicted, right? So that's where we get into challenges, but there are few ways we can still do it. um, uh, but that is not a standard practice which is generally followed. Okay, standard practice is to actually do the forecasting unit by unit and kind of recursively progress and achieve your results. The only challenge I think you or any data scientist must be careful with is that when we are doing the forecasting, we want to make sure that the forecasting is reasonably correct, right? Otherwise, if let's say your next week forecasting has errors, then those errors will propagate, right? So because once you have forecasted, that forecasting becomes part of the normal data, and that is used for the next forecasting, right? So if your forecasted value has errors, then your errors will start propagating and your model results will not be very good. Okay, so this is something which we need to take care, but otherwise I think this is what actually happens when we do forecasting, and that is how the forecasting is different than any other supervised learning methods like prediction or anything else. Okay, so I hope it's clear. We can come back to it if you have questions later. So let's move on. Now, in the previous slide, we looked at the train and the validation, right? And based on that, we kind of scored the model and looked at the performance. So it could be RMSE, right, root mean square, or it could be MAPE, right, mean error percentage. So it could be any metric, but that's how we do it, right? Now, uh, so this is one way, but in order to make sure that your model actually works uh, across the length of the span of the time series, there is I think it is advisable that you do the validation on the multiple size windows. Okay, now that multiple size windows can be really up to you, but it should just follow one constraint, that the validation should always kind of succeed the training, because it is a time bound data, it's a temporal data. So I think uh, cap kind of extracting the validation data set randomly from anywhere actually does not make sense for the time series. So time series always go in an orderly fashion. So it's always advisable that you have your validation data which is succeeding your training data. Okay, so as you can see in this picture, there's so many different ways you can actually do the validation. And you can choose the window sizes also. Your training window sizing and the validation window sizes could be different as well. So it's all depend on your creativity, depend on your data. When you look at your data, you see what are those local spikes, what are those global trends, and based on that you can set your validation window, and you can actually do some sort of a cross validation. Now, whatever score that you get through cross validation, and you might average it out, and then you can define the performance of that model, right? So your model may give you a very less sort of RMSE for one validation window, may give you higher at the other validation window. So that means that you may have to still look for other models, other strategies to see how can your model kind of work well across the entire span of the time series data. So again, this becomes like an experimentation field for the data scientist, and you can apply a lot of good ideas here. Okay. Now moving on to the feature engineering. Now, where are the features here, right? So most of the time, you know, this type of question is asked. Where are the features? How we can apply machine learning. Because there's only sales data here, right? And that is a Y. Now, how can we get the X, right? So coming back to the feature engineering. So there are multiple ways we can create features. One of the very powerful feature engineering area is decomposing the date, decomposing the time itself. So we can decompose, we can, extract year, month, day, and maybe some more features like what is the week number, what is the quarter, week of the month. There could be few more kind of features that you can extract from the date field itself. Now, how does it help? Actually, it helps you build the seasonal connection. Now, if you remember the seasonality in your time series when we used the statistical modeling. So seasonality is nothing but week to week or month to month, right? Year to year. So that kind of stuff, right? Now, when you tie your model, machine learning model, with these uh, features which are coming from the date field, you're actually trying to simulate the seasonality. Okay, so they become actually really powerful feature. In fact, I've seen many solution where people have only decomposed the date and build a machine learning model, right? They have not done any additional feature engineering. This is the only feature engineering they do, and they can build a machine learning model which can reasonably fit well. Okay, so keep in mind that this is very important feature engineering, and it will give you a flavor of seasonality or cyclicity in the data, and it will keep your errors low, because most of the time the errors are originated when you have kind of cyclicity in the data, right? So this is one way we can create the feature. The other type of feature engineering is also quite interesting. It's about creating, um, it's about transforming your time series into supervised, right? So supervised learning, you have few axes, independent variables, and that result in Y, which is your kind of uh, dependent, right? The outcome variable. So how do we get the access here? So one of the ways we get access is through calculating lags. So lag is nothing but a previous value, right? So time series is is like a time dependent. It's like a trend, right? It's like a trend. It's not a cross. It's not like at any given point in time, I have these many data. No, it's like point by point we have the data. So most of the time, there is a correlation. We do not call it as a correlation, but we call it as an autocorrelation, because the time series correlates with itself, right? So it does not, we don't have to have an external variable, right? It actually correlates by itself. So in order to simulate that behavior, we actually create the lag feature. So as you can see here, so I do not have the sales data here, but you can assume that the first item of the sales data would be 27.4. And that's how you see the lag. So lag is nothing but looking at the previous value. Okay. And when you say lag 2, that means you're looking at the previous 2 values, previous 3 values, and so on, right? So you can actually build many lag features, in fact, right? And you can experiment, right? You can take up an evolutionary approach that you build, let's say 10 lakh features first, run your model and see what are the most important lag features. And if your most important lag features are farther apart, let's say 8, 9, or 10, then you might like to add few more lag features, right? Because you feel that, the farther it is, it's giving more impact to the model. So you can add few more additional lag features, right? So you can take up an evolutionary approach in that case, right? So this is one way we can generate the feature. Other is, we call it as a rolling window. So rolling window is nothing but taking an average of last few values. So maybe an average of last previous two values, let's say t minus 1 and t minus 2, right? Or previous three values, 1, 2, and 3, and so on. Again, this is there is no foundation, there's no limitation. You can have as many rolling window variable as you would like to have. Now, what is the advantage of rolling window? So the advantage is that you through by averaging the last few points, you're trying to reduce the effect of variation, right? You're trying to smoothen out the entire data. So that means you're going closer and closer to the trend, right? You're trying to remove a lot of noises or a lot of local effects, and you're trying to get closer to the trend. So rolling window is a very powerful feature, and that actually captures the trend in your data. Now, the smaller rolling window will capture the local effects, right? How is the local trend? And the larger rolling window size will actually capture the long-term kind of a trend. So it's again a very powerful feature, right? Now, instead of rolling means, we can also have weighted means, or we can also have exponential means. So you can experiment as you wish, depending on the problem statement, right? So the weighted means would be like, you can give more weights to the points which are closer to your current timestamp. Let's say if you are at t, you might give more weight to t minus 1 and t minus 2, and less weightage to the points earlier than that. So again, this becomes like an experimentation field for us, and we can build as many features as we could. And not only that, we don't stop here. We can build features like standard deviation. We can create, so I think I have the next slide. So we can create a lot of interaction. So let's say 2 lakh features, we can create difference. We can build, division, multiplication, standard deviation. So maximum, minimum, it's up to us, uh, depending on the problem and that we are dealing with. We can actually build as many features as we could, and that is the beauty, because that is where the machine learning is so strong, right? Because we can have so many features, and we can not only have features alone, we can actually build interaction. We can build like cross features from those features, and try to see the impact of everything on our forecasting or on our predictions. Okay, so these are some of the feature engineering tricks, techniques that you can use when you build your machine learning model. Okay, so we have looked at some of the pre-processing stuff. We have looked at the feature engineering. Now let's jump into the model building. So that the XGBoost, right? So XGBoost is like a technique where it's it actually builds on top of, so it learns, right? And then it evaluates and look at some of the features where the score is not very good, and we call it as the weak learners. Then it actually focuses on the weak learners and again builds the model. So it is a step-by-step model building approach, right? So it will look at the leaves. If you look at the tree structure, so it starts looking at the leaves, rather than the levels, right? And leaf by leaf, it'll start building the model. Okay, so XGBoost actually works very well in context of the time series. I would say it is one of the most preferred method when we build the time series forecasting. Okay, there are a few more methods. For example, CAD boost, or simple gradient boosting, or we can also use the support vector regressor. We can also use neural networks. So there are multiple methods which we can apply. But my experience is that if you apply XGBoost first, uh, there are many advantages. One, that it fits very well in the time series context. Second thing is it's pretty fast. Okay, it will tell you. It could tell you, what are the important features. And as I was telling you earlier, that if you like to add more features by looking at the feature importance, data, then you can actually go back and add those features and run it again. So you can make this entire experience as iterative experience, and you can build more robust model using this approach. Okay. So that's what I've applied here. So first I've applied XGBoost, and let me show you some of the results that I've got. So you can see that the lag features, the rolling mean features, and some of the time, features, date features are also uh, kind of appearing, in top 15 features. So you can see that by looking at this kind of feature importance, you can easily guess that this is a highly non-stationary kind of environment we're dealing with. So everything matters here, right? So that's what it gives. And if you look at the right hand side window, where you have the blue color and the orange color. So the blue color is the actual, and orange color is the forecasted. So this is like training and validation piece. So we have not gone into the forecasting yet. This is about sort of measuring the accuracy of a model. So you can see that it actually fits quite well with the original time series trend. Okay, so overall, I think it has done well. Now, if I have to look at three different approaches that I have used here, and this is just for this presentation. As I said, there's no limit. You can actually use a lot of other modeling techniques and generate more uh, models and compare them. So as you can see that the XGBoost and CatBoost, they actually kind of fit quite well. So for example, it's going up, down, down, up, down. So there are a few areas where it does not fit exactly the trending curve, but I think it is because I have not done the cross validation in the interest of time. So that's how I think if I had to do the cross validation, it might get better. But against the GBM model, I think the GBM model looks slightly off. It kind of trend goes up and down, but it does not actually fit as good as the other. Okay, so let's move on to the next. Now this is the forecasting output by using these machine learning models. So forecasting is something, if you remember, we discussed in the previous slide where we were forecasting week by week, right? 1 week at a time. So this is the output of that approach. Okay, so you could see that it looks quite reasonable. It kind of follows the trend. And looks reasonable. A GBM model, it it kind of looks also reasonable, but really, for example, towards the end of it, I could see that it starts to go down. Here also it starts to go down, but in this case, I think it still remains up. So uh, again, this is the forecasting horizon, and we really don't know what is right and wrong. So most of the time, what we see is that by we first look at the validation error and pick up the models which may have less validation error, right? And then we look at the forecasting trend and kind of look at the forecasting trend for those models. And if those trend more or less look similar, then I think generally what we do is we ensemble the output of those models together. So basically, we kind of average the values which we get from both these models and use that ensemble model to actually generate the forecasting. Okay, so and that makes sense because when we do the ensembling, you actually trying to reduce the overfitting nature of your model outcome. Okay, so it actually makes sense for most of the cases. All right, so I think we are coming towards the end of our presentation, and we will look at the coding piece. But I would like to show you some of the output when we look at the time series customer wise, at a lower level. So you can see that now I'm plotting the time series customer wise, and you can easily notice different trends. So this customer has slightly increasing trend, and this customer 33 is kind of flat. But you can see those blue versus orange, right? So the orange actually lines up pretty well. So it so the previous slides we saw the forecasting at the aggregate level, right? So we see at the top level, but here we are seeing at a customer level, and every customer has a different sort of trend. Okay, so this is about the sales, but you can see that it's kind of lining up pretty well, and it's all happening in one single model. So we are not created like 4,000 different models. Okay, so now you can see the flavor of the product. So this is product wise, and you see the similar kind of stuff here. And then you can also do a customer and product group. So you can say that I would like to look at every customer with every product, right? So that kind of analysis also we can do, and we can look at how our sales projections will look like against every customer and product groups. Okay, so that's about the machine learning stuff. Now, as I told you that this is an area which is actually picking up quite a lot of interest, not only in the real world but also in the research field. So um, so so people are experimenting with a lot of different kind of features. So for example, I've seen some papers where people have actually experimented with wavelets or some sort of kernels, specific to the problem they're dealing with, and they actually add value to the outcome. So this is one area which can be experimented, and the other is the neural network. So all the convolutional recurrent. In fact, I've seen few papers where people have actually combined all these three neural networks together in order to do a forecasting for the time series. Okay. Now the neural network actually works in the same way like we have seen the machine learning. So neural network also tries to use the lag variables and try to set up the problem as a supervised learning problem. And the only advantage there is that we can add layers to the network, right? And then we can have that non-linearity infused into the network, and we can learn something else which we may not be able to handcraft in terms of features, right? So neural network gives you some auto features which sometimes difficult to learn on your own, right? So that's the advantage people get out of neural network. So with that, I think we are done with our presentation. Now I will switch to the code. So I'm now sharing my R studio. I hope you can see. So So before I run the code, I will tell you some of the functions, which I've created, like a reusable piece of code, which you can use. So for example, we talked about decomposing the date. So this function will actually decompose the date into month, week number, day, whatever you see upon on the presentation. Now, as I told you, this is not limited, so you can add some more stuff to it, right? You can add more features to it, but the function will take care of it. And then this function will create the lags. So basically, um, it takes the input of what is my starting lag and how many number of lags I would like to create, and automatically build those lag variables. So there is a very cool feature in R called set names. So it will actually create the function, it will build the function names for you. And then we can use the func method in R to actually make those function go live, and give you a calculation and give you an output. So you can see that hardly 6-7 lines of code, we are actually able to create so many lag variables, okay, in a loop. Same, so I'll come back to this. Same with the rolling window. So the same, using the same trick, I think we can create the rolling window. So there is a function called roll mean R. So it basically creates the mean of the previous two values or previous X values, right? Um, and then we will have to take a lag, because that outcome goes sort of one step ahead. So by taking a lag, you make sure that it is captured as part of your context. So that's how we build the rolling window. Now, as I said, this is about the mean, but you can actually have exponential mean here. You can also have weighted rolling window means here. It's again an experimentation area for us. So you can even have your custom function and create some other cool features in terms of rolling windows. Okay, and then there are functions related to calculating the standard deviation, or let's say previous two values, three values, and X values. And then this is about the interaction, additional lag features as you see here. So here, what is happening? We are creating the standard deviation of the lag feature, let's say 2 or 3 lag feature. We are creating max of, let's say, 2 or 3 lag features, difference, division, and so on. So as I said, these are some of the methods that I have created in order to do the feature engineering. But again, it's not limited, and you can actually add quite more. So with that, let me just go back to the program. So let me just load all the libraries and start running. Okay. So in this program, in the interest of time, I've started capturing the lag feature from lag 1 onwards, and uh, 1 to 8, so 8 lag features. And the rolling means actually 2 to 10. So, and the forecast horizon is about 12 weeks. Now, all these variables can be changed, right? So you can create, if you change from 8 to 10, you can create 10 lakh features. If you change from 10 to 20, you can create actually 20 rolling window means. Okay, and forecast horizon, if you change to 24, you will get forecast for 24 weeks. So it's all flexible, and that's the advantage of it. Okay, so let me just run that. And this is how we have sourced all those functions that we discussed before, all those utility functions. Now we're going to read the train data. Okay, so we have around 4,20,000 data points, right? If Let me convert the week to the date, and then we can look at the glimpse of the data. So you have few more variables in this data set, but I think later on we will ignore those. But the key variables which we need to see are like week, product, holiday, customer, and sales. Okay. Now other variables also we can add depending on the time and everything. So for this demo, I have removed them, but like how we are creating the lag variables for the sales, we can actually create the lag variables for the other uh, acts you have in your data. So you can create lag variables for attrition, rolling mean variables, all those feature engineering you can do for all the other uh, data points that you have. Okay, but in the interest of time, I have just skipped those variables at the moment. Okay, then what we are doing, just removing, just identifying the sales if there are some negative. So it's all about pre-processing step, because sales are generally not negative. So if there are negative sales value, then so we are just transforming them to zero value. So here I've not removed those rows that have negative value. Instead, I have just changed the value to zero. Okay. All right. Now, in this particular case, what I've done is, again, it's a part of pre-processing step, uh, because some of the customer and product combinations, we may not have a good amount of data, right? We may not have data for, let's say, 6 months, 1 year, or 2 years. So we may have only a small amount of data. So in this particular case, I'm just throwing off those cases, because if you don't have sufficient data, I think it's not easy to do the forecasting as well. So minimum length period which I've considered is 20 weeks, but again it can be different for the different context of the problem. Okay, so this is about the train, and now we will read the test. Now if you see the test, you will not find the other variables in the test, right? You will only have the variables which you know in the future. So for example, customer, product, you anyway know what are those customer, products, and week and holidays. So your test data will not have those additional features what you noticed earlier, like attrition, discounts, and all that, because those are all future. Those you will not know, what are their values in future, because that future is not arrived, right? So those things will not be there available as part of your test data. Okay. Now here we are just combining both of them, test and train. And what we have done is we have only picked up those product and customer, which we might have you know filtered in the training, because some of the customer product might have been discarded when we did this filter operation. So in order to match the data with the training data, some additional steps we have executed here, so that we have the right kind of data in the combined data set. All right, so now here is the juice of everything. So here we decompose the date features, right, and create those autoregressive and moving average. I just call them as autoregressive moving average because they kind of simulate that behavior. And then we create some of the additional lag features that we discussed, like division, max, min, that kind of stuff. So let's create them. So you can see that we build those lag features on the sales, and then we have also built the rolling mean features on the sales. Okay, great. Now after that, we'll remove if there are NA, because sometimes when you divide two variables, there could be some exception. So we'll remove, and then after that, I think the size, we still have a pretty good size, like 3.6 lakhs. All right, so as we mentioned, we'll drop some of these variables like price, discount, attrition. So we'll do that. And then we will prepare the data for training and validation, okay? So we will split the data at this particular date. Now this date can be flexible and we can experiment with it. And then after that, we kind of fit the XGBoost model and we train the model. Now I've used here almost like 500, but I think it will take some time. So I'll change it to 100 here and let us run this. So your train and validation has this size, 3,62,000. And now we are going to fit the XGBoost model on the train and validation. So you can see that, one of the best thing what we see in XGBoost is it tells you, what is the train and the validation score, and you can easily see if there is an overfitting, right? So if your train score is really, really low and your validation is relatively high, then I think you can see that, maybe your model is overfitting. So let's see what do we get here. So I'm running only for 100 trees, not more than that, in the interest of time. Yeah. So I think 100 trees, it did a pretty decent job. It does not look like an overfitting case because validation is actually lower than your training. So with that, we will go ahead. But if you put 500, actually, the training score will also come down and the validation score will also come down, and they kind of match up quite closely. Okay. Now, let's look at the importance. Yeah. So I think this should look similar to what you have seen. Now here, importance, I have plotted 20 top 20 features. In the presentation, I had only 15. So you can see still the lag and rolling means, they kind of top the chart, and week number holidays, they also appear. So they kind of bring the seasonal effect in the model. All right, so we'll predict. We look at the RMSE. So yeah, so here the RMSE is slightly high because we have used only 100 trees. But in the presentation, if you noticed, the RMSE was about 8.7. Okay. So now, as a standard practice, we see how our data kind of looks, the actual and predicted value. So you can see here that it actually looks quite good. So it's a dense, a lot of points because there are a lot of time series here. But if you look at the overall trend, I think it actually fits very well. Okay, it actually it's very close to the actual values. Okay, now let's look at the residual plots, because through residual plots we understand whether it's random, it's randomly distributed, or it is showing some kind of a trend, and that's very important to study, because if you see some sort of a trend, that means that your model may have some additional dependency on some additional variables which you may not have created, or you may not have at all. So that is something which you may have to check it out. So here also it looks random. I don't see that it is following some sort of a trend or anything. So overall it looks good. And then what I've done here is I've saved the prediction to an output file. so that I can analyze it. Now, as I said, it's very difficult to create plots of the output because there are multiple time series involved here. There is a time series for every group. So either you can use Shiny application, right, where you can build a drop down menu and then look at each and every output. Here what I've done is I have used the Tableau, right? So I have sort of used the Tableau, and in Tableau actually you can see um, how the prediction look like, and you can actually go every customer wise or every product wise, and you can start looking at it. Okay, so Tableau is another good way when you're trying to inspect, because there are multiple time series involved. Okay, so this is about the validation. Now let's look at the forecasting, and that's where the magic happens. Okay, so here what we have done is we have looked at 12 weeks. Like we had data only till uh, 1st of August 2018. Now we have started to look at 15th onwards. Okay, 15th of August onwards. So that's why you see that the for loop is starting from 15th. Now what happens before I run the for loop, I tell you what's happening here. So we kind of get the data. So we are going to do prediction week by week, right? So we get the data 15th of August and before. So because we are not really looking at any further down. So we get the data here, and then based on that, we generate those lag features here, and then we use the same model to predict, and then we attach that data with the original data. You remember the total data set that we created with training and test, and then we run the loop again. So let's run it. So one by one, it's going to add the prediction. Okay, so this is like second week, it has added the prediction, and so on and so forth. So until this is running, we can look at some of the predictions. So this is how it looks for XGBoost. And if you look at product wise, customer wise, all these things we can inspect through the Tableau. All right, so I think this is pretty much what we have in the presentation today. So what we have seen is how the machine learning can be applied on the time series forecasting. And I'll tell you, in my experience, a lot of people, they actually have no idea how to do it. Okay, so and how do we create the feature engineering, and how can we even expand the feature engineering using the evolutionary approach? Like we use XGBoost, we can start looking at features, and we start adding more feature engineering to our model and start building more robust model. And how do we forecast? We forecast in recursive fashion, week by week, month by month, or day by day, depending on the frequency of your data. All right, and code, it's pretty straightforward. I think it's no big deal. So with that, I think I'm done from my side, and I'll open the floor for the questions.
Okay, so the first question that we have is XGBoost mainly used because it takes care of variance and bias?
Well, that any tree-based algorithm is actually an ensembling approach, and definitely it tries to take care of both bias and the variance. But the boosting algorithms are actually slightly different. They basically um, focus more on the weak learner piece, right? So they kind of build the strength of the model tree by tree, and that is why I said, I ran it for 100. You may not get very good accuracy when you run it for 100, but when you run it for more, you will get a better accuracy. So yes, it basically evaluates the strength of the model tree by tree, and it tries to improve the weak learners in the model step by step. I
Okay.
hope that answers the question. Yeah.
I hope that is answered. So I'll move on to the next question. Next question is, how do we decide how many features are we adding in the models? How many lag features and how many rolling features?
Yeah, so it's very interesting question because it's you will not do. I mean, as a data scientist, we would first like to look at the visualize the data first, right? Uh, so my suggestion is that try to visualize the data and try to look at what kind of ups and downs, the trend, the shape change, and the local changes that you see in your data, and then try to build a hypothesis by looking at the data to start with. If you see week to week changes, then it's good to have rolling mean features covering that, or the date features covering that. So likewise, you start with some assumption by inspecting your data, and then, as I said, XGBoost. Why it is so nice is that you can throw some initial features with the XGBoost and see the results. And as I said, if you see that lag 10 or 11 are showing importance more than the lag 1 and 2, it's a clear indication that it's good to add few additional lag features with a further away. So you can actually add more features that time, and then again iterate your model one more time, and like that you can keep doing. So it is an experimentation area, but you don't have to really start with a huge number of features. So you can start with some small number of features based on your initial understanding of the data and the domain and what you visualize, and then use the machine learning model and make it as an iterative process, right? Add more features step by step.
Okay. I hope that is answered. Okay. Perfect. So the next question is, how to convert POSIX CT to desired date variable.
Uh, Convert what?
So how to convert POSIX to desired date variable?
6 2.
POSIX, POSIXCT.
Acha, pox sit. Okay. So I think it I think it means like some sort of a date format, pox sit. So yeah, you can use. So basically, what we are doing here is we are converting the string to the date variable. Okay, because the data when you load the raw data that you load in R, your date will come as a string, or it might come as a factor, but it may not come as a date sort of uh, data type, right? So so you can use Poxit also. You can use a standard as.date functions also, and there are a few more functions available in libraries like LookRedate and etc. You can actually use those functions. Basically, the end goal is to convert the date variable in the date data type in R.
Okay. Okay. So I hope that question is answered now. I'll move on to the next question. Where is seasonal arima used?
Well, this is uh, machine learning stuff. But if you're interested in knowing where is seasonal ARIMA used in the ARIMA modeling, then you know if you've gone through the ARIMA modeling, you will have 6 type of features in ARIMA modeling, right? Small p, d, and q, and then big p, d, and q, right? So the small ones are actually um, sort of giving you a local effect, and the big ones are actually giving you a seasonal effects. So if you go through the ARIMA modeling, the big P and Q are actually going to give you the seasonal effect.
Okay. Thank you, Praveen. So the next question that we have is there a difference between frequency and periodicity for a time series?
Well, periodicity, we generally say when the time series is some sort of stationary time series, because for non-stationary time series, the periodicity can be can be many, right? While the frequency is nothing but the time gap at which you are receiving the data. So, for example, here I'm receiving data every week. So, week becomes my frequency. But when we talk about periodicity is more of uh, looking at the time series and then analyzing, what is the periodicity, because it really depends on wavelength, etc. And for non-stationary time series, there could be multiple wavelengths, so there could be multiple periodicities.
Okay, perfect. So the next question: how can we make sure to avoid the error for current prediction to be cascaded for future predictions? Would checking for good RMSE and MAPE be good enough to ensure less errors?
Yes, I think that is a pretty good starting point, and I would add that you do a cross validation. Along. Don't. I mean, in the interest of time, I have only done only one short validation. Only one time, but when we are working on the real time projects, I think you have enough time to actually experiment. So I would say that along with that, you do cross validation. You try to evaluate the strength, the score of your algorithm at a different time period. Try to move that window from left to right and try to evaluate the performance at different time period, and then try to gauge the score of your algorithm. But yes, that will be a good starting point, uh, in order to make sure that the errors are low. In the end, what you can also do that, as we discussed, that cat boost and xg boost were kind of giving a similar predictions. Maybe there are few areas where the cat boost was over predicting, might have over predicted slightly. So if you see that kind of scenario where one algorithm works uh, better and other works worse, and for other particular time window it is reverse, the other one works better and the previous one works worse, then what you can do is you can actually average, you can ensemble these two outputs and then use that as your prediction for the next week, and then again keep on doing this recursively.
So, Praveen, what we are doing currently, we are working on a project. I'm part of a team, and we are trying to predict the stock price trend up or down basis, the technical indicators. And those technical indicators are pretty much the same variables what you have used here, like lag, rolling means, and all those things. And then there are some high definition technical indicators also. So and we are using machine learning like extreme gradient boost and all other algorithms. Now question is that these technical indicators are actually derived from the stock price itself, and so basically X is dependent on Y, you see, right? I mean, unless we don't know the price trend or historical price, we can't derive these technical indicators. And we are using these technical indicators as dependent variables to predict the price. So we built the model, training, testing, all done. The accuracy looks good. Now my question is, how do we productionize this model? In order to productionize this, I need to have the data, which is in my X variables, and those X variables are actually dependent on price. So if I know the price itself, what will I do with predicting the trend? Have you come across this kind of situation in stock market prediction, and how to go about that? I mean, I can use a forecasting method to first calculate the price for the future days, and then derive these technical indicators and then predict the trend. But that will be like, doing the obvious. So that's where we are lost. Do you have any guidance or direction in this, Praveen?
I mean, uh, if I know everything about stock market, I would be very rich. So, keeping that aside, I think what you're trying to do is, if I understand correctly, you're trying to forecast. Actually, you're not trying to predict because you're going into the future.
Yes.
Yeah. So you have to treat this as a forecasting problem and not a prediction problem. Okay. So I think you have to follow this approach, what we just discussed in this talk today.
Right.
So go one by one, day by day. So forecast the prices next day using the lag variables or other features in the previous days, because that information you already have, right? The lag features, the previous day information, or previous day's information you already know. So use that information and forecast the price for the next day, and then use that as part of your data, and then forecast for next, and keep on going like that.
Okay, Praveen, thank you. Yeah, that's
Yeah.
what I guessed. We will have to move to forecasting rather than prediction. Yeah, thank you.
Yeah, no problem.
Thank
Thanks.
you, Rahul. Thank you for the question.
In this tutorial, we have learned about what is time series forecasting. How can you use your past data to forecast your future? I hope you all like the video, and please do let us know in the comment section what you feel about this video as well. And before complete the video, let me tell you that Great Learning has come up with a brilliant idea, that is Great Learning Academy, where you will learn about almost 80 plus free courses, and after complete your course you can claim your certificate as well. And if you want to do these courses in a mobile application, that is also possible using Great Learning app. Thank you so much.